am Nurul Nordin from UMPSP STEM Lab, the Faculty of Electrical Electronics Engineering, University Malaysia Pahang Al Sultan Abdullah, the instructor for this course.
Hi, welcome to Micro-credential number 2, RTL Design and Synthesis. In Micro-credential 1, we previously learned how to describe the hardware. Now we focus on how that code is transformed into physical reality. This Micro-credential number 2 module is about the bridge between your Verilog files and the actual silicon on the FPGA. We are moving from does it work in simulation to how does it perform in hardware. So basically, you have learned the basics of digital logic, but now it is time to architect the real system. In this Micro-credential module, we are exploring Register Transfer Level, or typically called as RTL, Design and Synthesis. This is where your code physically transforms into synthesizable hardware. In this Micro-credential series, there are 4 chapters associated with it. We will start Micro-credential number 2 with chapter number 5 and 6, where we build the foundation. In the context of digital system design, RTL stands for Register Transfer Level. It is the level of abstraction used in describing the operation of a synchronous digital circuit. At the RTL level, a designer defines the circuits by specifying the registers where the data is stored, typically flip-flops, the combinational logic, the operations performed on that data, such as adders and multiplexers, and the data transfers, how the data flows from one register to another. RTL is the sweet spot of digital design because it is the highest level of abstractions that can be automatically converted or synthesized into actual hardware gates. When you write Verilog in this course, you are primarily writing the RTL code, which the Intel Quartus software then translates into the physical circuitry on your DE10 Lite FPGA. In this chapter 5 and chapter 6, we'll map out both combinational logic like adders and multiplexers and sequential logic powered by flip-flops and shift registers. We also master the brains of our control system, the finite state machine, or typically called as FSM. You will learn the coding best practices to build both more machines, where output rely only on the current state, and mini machines, where the output react instantly to the inputs. But before we ever touch a physical chip, we must prove our design works. In chapter number 7, we dive into the functional verification workflow using tools like Model Sim. We will write test benches, apply virtual stimuli, and perform deep waveform analysis to hunt down logic bugs and validate our system in a safe, simulated environment. Once the logic is flawless, it is time for the heavy lifting, logic synthesis. In chapter number 8, the Intel Quartus tool translates your RTL code into gate-level netlist, mapping your design directly onto FPGA's physical resources. But does it run fast enough? That is where static timing analysis, or STA, comes in. We will analyze digital system performance by examining critical path, setup and hold times, and timing slack. If your circuit is too slow, you will learn to optimize the maximum operating frequency using powerful techniques such as pipelining and retiming. Throughout this Micro-credential, you will go through lab number 3 and lab number 4. In lab number 3 and 4, you will deploy your designs straight to the DE10 Lite FPGA board. You will build a physical 4-bit adder and even design an FSM to control a satellite communication link simulation. By the end of this module, you won't just be writing code, you will be analyzing, verifying and optimizing true high-performance hardware. Let's get started.
Hello, hi. I am Nurul Nordin from UMPSP STEM Lab, the Faculty of Electrical Electronics Engineering, University Malaysia Pahang Al Sultan Abdullah, the instructor for this course.
Hi, welcome to chapter number 5. Today, we are taking a massive leap into our FPGA journey as we explore Register Transfer Level, RTL Design. At this level, we are describing the true behavior of our digital circuits in Verilog by focusing on data transfers between registers and combinational logic. Let's break it down into two main pillars. First, we have the combinational circuits. The golden rule here is that they have no memory. Their output depends only on the current input values. Think of them as the pure maths and routing center of your design. You will build multiplexers to select data pathways, decoders to translate modes and instructions, and encoders to compress sensor data. And of course, you will create fundamental arithmetic units like the adders and ALUs to do the heavy lifting. But what happens when our system needs to remember something? That is where sequential circuits comes in. Unlike combinational logic, sequential circuits retain their state. Their outputs depends on path history and are perfectly synchronized by a clock signal. The most basic 1-bit memory elements are flip-flops, like the D, T, JK, and SR types. When we group them together, we can build counters to track times and discrete events, or shift registers to move data serially, a crucial feature for space-constrained communication system like the Lilacs 5 applications. In summary, Chapter 5 gives you the raw processing power with combinational logic such as adders, multipliers, and muxes, and introduces the basic concept of memory with flip-flops, while Chapter 6 takes those flip-flops and combinational blocks and wire them together to create an FSM, the intelligent brain or control path of your system. We are now entering the combinational logic. In these circuits, the output is determined solely by the current combination of inputs. There is no memory, no history, just pure logical processing. To build these systems, we rely on 7 fundamental primitives. First, the AND gate. Think of it as a series connection. The output of Y only goes high if both input A and input B present. In Verilog, we instantiate this using the AND primitive. First, the AND gate. Think of this as a series connection. The output Y only goes high if both input A and input B are present. In Verilog, we instantiate this using the AND primitive. Next, the OR gate. This represents a parallel path. The output Y is high if either A or B is high. We describe this with the OR primitive. The exclusive OR is unique. It only outputs a 1 when the inputs are different. The gate is mathematical heart of arithmetic circuit like adders, which we will explore later in this module. Then we have the NAND and NOR. In the physical world of CMOS fabrication, these are often more efficient to build than the standard AND or OR gates. In Verilog, we simply use the NAND and NOR primitives to describe these inverted behaviors. The exclusive OR is an equality detector. It outputs a 1 only when A and B are exactly the same, either both zeros, either both 0 or both 1. This is a critical component when designing a digital comparator. Finally, the NOT gate or inverter. It is the simplest combinational element, taking a single input and producing its logical opposite. If you have an active high signal that needs to be active low, the NOT gate is your tool. Every complex combinational circuits we will study, from multiplexers to decoders to arithmetic logic unit, is simply a strategic arrangement of these 7 gates. Now that we know our building blocks, let's look at how we combine them to solve complex logical problems. A good example to kickstart is adders. Before we build the adder circuit, let's look into the mathematical operation. In binary addition, just like the decimal mathematics you learned in school, we use vertical addition. We add our augend and our addend column by column, starting from the right. Notice that what happened when we have 1 plus 1. The result is 2, 1, 0. The 0 is maintained at the result, and we generate a carry. We call this as carry out. The results or sum is 0, and we generate a carry, that is a carry out. The carry out from one column becomes the carry in for the next. This simple process is the foundation of all digital computation. But to a computer, this isn't math, it's logic. When we only need to add 2 single bits, A and B, without worrying about a previous carry, we use a half adder. Look at the truth table here. When we add 1 and 1, our sums become 0 and our carry becomes 1. If we map this to a K-map, we see 2 distinct patterns. The sum follows an exclusive OR. It's only 1 when the inputs are different. And the carry follows an AND logic. It's only 1 when both inputs are 1. So a half adder is simply one exclusive OR gate and one AND gate working in parallel. But it has a limitation. It cannot accept a carry from a previous stage. To handle a real-world addition where a carry might be passed in from the right, we need the full adder. The circuit accepts 3 inputs such as shown here: X, Y, carry in, and resulting into 2 outputs, sum and carry out. By analyzing the truth table and K-map, we derive slightly more complex architecture, a full adder. A full adder is essentially 2 half adders joined by an OR gate. It produces sum and carry out, allowing us to chain these modules together to add numbers of any length, from 4 bits to 64 bits and beyond. Now that we have designed a single full adder, how do we scale it up to add large numbers? Say for example, to add 5-bit numbers as shown here. To do so, we simply arrange 5 full adders in a chain. This configuration is known as a ripple carry adder. Notice how they are connected. We take the carry out of the first stage, full adder number 0, and feed it directly to the carry in of the next stage, full adder number 1. This continues all the way to the final stage. This is called a ripple adder because the carry bit acts like a wave in a pond. The second adder cannot finish its calculation until it receives the carry from the first, the second. The third waits for the second, and so on. The carry must ripple through every single stage before the final sum and the carry out are valid. While this is a simple and elegant design, it introduces a propagation delay. The more bits we add, say for example 32 or 64 bits, the longer we have to wait for the carry to reach the end. This critical path is exactly what we will analyze in the micro-credential number 3 when we talk about timing. Keep this physical chain in mind, whether we use structural, data flow or behavioral code. This ripple carry structure is what the hardware is ultimately building inside your FPGA. Let's look how to implement a 4-bit ripple carry adder in Verilog using these 3 modeling styles we discussed earlier. Each styles offer a different balance between control and convenience. In structural modeling, we built the 4-bit adder exactly like a physical circuit board. We treat the full adder we just designed as a sub-module. To create a 4-bit version, we instantiate or place 4 of these full adders and manually wire the carry out of one to the carry in of the next. This is the most transparent way to see the ripple carry architecture, mirroring exactly how gates are connected on silicon. In data flow modeling, we use the assign statement to describe the flow of data through Boolean or arithmetic expression. Let's look at 2 ways to apply this. First to a single full adder, then to our entire 4-bit system. For a single full adder, we translate our K-map results directly into code. To find the sum, we use the exclusive OR operators. A, exclusive OR B, exclusive OR Cin. For the carry out, we use a combination of AND and OR logic. This is highly efficient for combinational circuits because it clearly maps the mathematical logic to the hardware. For a single full adder, we translate our K-map results directly into code. To find the sum, we use the exclusive OR operator. A exclusive OR B, exclusive OR Cin. For the carry out, we use a combination of AND and OR logic. This is highly efficient for combinational circuits because it clearly maps the mathematical logic to the hardware. Now, watch how data flow modeling simplifies things when we scale this up to 4 bits. Instead of writing out every individual gate for our 4 stages, we use Verilog's built-in arithmetic operators. By using the concatenation operator, the curly braces here, we can group our carry out and sum together as a single 5-bit results. We simply say Cout and sum equals A plus B plus Cin. Behind the scenes, the Intel Quartus synthesis tool sees this plus sign and automatically implements a 4-bit ripple carry adder using the optimized logic resources inside your FPGA. You get the same hardware results with much cleaner and more readable code. Behind the scenes, Intel Quartus synthesis tool sees these plus signs and automatically implements a 4-bit ripple carry adder using the optimized logic resource. Using the optimized logic resources inside your FPGA, you get the same hardware result with much cleaner and more readable code. Behavioral modeling is the most flexible way to write Verilog. Everything happens inside an always block, which triggers whenever our inputs change. Let's look at 3 different ways to describe our 4-bit adders behaviorally. The first and simplest style is the arithmetic approach. Just like in data flow modeling, we use the plus sign. However, because we are inside an always block, we are describing the procedure of addition. This is the cleanest way to write code. It is easy to read, easy to debug, and let the synthesis tool decide the best way to build the gates. Secondly, we have the if-else approach. This is where Verilog starts to feel like a traditional software programming. We can describe the addition by checking conditions. For example, we could write logic that says, if the inputs are at the maximum value, then set the carry out high. While this is more worthy than a simple plus sign, it is incredibly useful when you need to add specific control logic. For example, you want to add a reset signal or an enable switch directly to your adder. Finally, we have the case statement approach. Think of this as a direct translation of the truth table into code. We list every possible combination of inputs and define exactly what the output should be for each case. While you wouldn't want to write out all the 512 cases for the 4-bit adder manually, this style is the gold standard for building finite state machines and decoders. It gives you absolute total control over every single input-output relationship in your design. Here is the key takeaway. Whether you use a simple algorithm, a conditional if-else, or a detailed case statement, Intel quarter synthesis tool will likely produce the exact same gate-level netlist. In hardware design, we choose the style that is easiest for human to read and maintain, while trusting the compiler to turn the behavior into the physical reality of our 4-bit ripple carry adder. Our 4-bit ripple carry adder works perfectly. But imagine we aren't building a 4-bit toy. Imagine we are building a 32-bit or 64-bit processor. Remember that ripple we talk about? In a 32-bit adder, the most significant bit, the 31st bit, has to wait for the carry to travel through 31 previous stages before it can calculate its final sum. This creates a massive propagation delay. In a high-speed computing, waiting for the carry to ripple is a luxury we don't have. It becomes a bottleneck that slows down the entire system's clock frequency. To solve this, we move from ripple carry adder to carry look-ahead adder. The philosophy here is simple. Don't wait for the carry, predict it. Instead of waiting for the carry to arrive from previous stage, carry look-ahead adder uses extra logic to look ahead and calculate whether a carry will be generated. It does this by looking into all the inputs simultaneously. The carry look-ahead adder works by defining 2 new signals for every bit's position. This signal is high if the current stage will pass a carry from previous stage to the next. For example, logic A exclusive or B. By using these propagate and generated signals, we can calculate the carry for the 4th, 8th, or even 16th bit almost instantly, without waiting for the bits in between. We are trading area for speed by making more gates and less delay. To understand how we can predict a carry, we have to look closely at the full adder truth table. If we isolate every row where carry out is 1, we notice a very specific pattern. There are actually 2 distinct situations that create a carry. The first situation is the most obvious, when both x and y are 1. In this case, it doesn't matter what the carry-in is. Even if carry-in is 0, 1 plus 1 will always produce a carry. We call this as the generate condition. These 2 bits are generating a new carry all by themselves. In our logic equation, we represent this as G equals to X and Y. The second situation is more subtle, when either X or Y is 1, and when there is already a carry-in. Here, the stage isn't creating a new carry from scratch. Instead, it is passing or propagating the incoming carry to the next stage. If X or Y is high, the door is open for the carry-in to pass through. We call this the propagate condition, represented as P is equals to X exclusive or Y. By looking at the truth table this way, we realize that a carry out is simply, did I generate a carry or did I propagate one of my neighbor? This insight is the secret sauce of the carry look-ahead adder. Instead of waiting for the neighbor to tell us if a carry is coming, we use this propagate and generated signal to look at all the bits simultaneously and calculate the results instantly. Now let's look at the mathematical model that makes the carry look-ahead adder so fast. By generating and propagating signals, we can write a series of recursive equations that predict the carry for every single stage simultaneously. For the first bit, carry 1, the logic is simple. We have a carry if we generate 1 at bit 0, or if we propagate the initial carry P0 and C0. This looks just like our full adder logic. But look what happens as we move to carry 2, carry 3, and carry 4. Instead of waiting for carry 1 to be calculated, we substitute carry 1 equation into carry 2 equation. Notice the pattern. To find the carry bit for bit 3, we only need to know the input stages of 0, 1 and 2. We are no longer waiting for a signal to ripple through a chain of gates. We are calculating carry 3 directly from the starting inputs. By the time we reach carry 4, the equation looks complex, but the hardware reality is incredible. This entire logic string can be implemented using a multi-level gate structure that resolves in just few gates delay. Whether you are adding 4 bits or 32 bits, carry look-ahead logic ensures that the last carry is calculated almost as fast as the first carry. This is the core of performance-aware design. By spending more space on the FPGA to build these propagation and generated logic trees, we gain massive amounts of time by reducing propagation delay. This is how modern high-speed processors maintain their gigahertz clock speeds. In short, the ripple carry adder is like a line of people passing a bucket of water. The carry look-ahead adder is like a supervisor looking at the whole line and telling the last person to get ready before the first bucket even moves. As we move into a more complex design on DE10 like later, understanding this trade-off between gate area and timing performance is what separates a student from an engineer. Now let's translate our mathematical equation into synthesizable Verilog code. We define module called CLA_4bit. Notice that in our inputs and outputs are defined as 4-bit vectors or buses representing our numbers A, B, and final sum. First, we declare internal wires for our propagate and generate signal. Using a single line data flow assignment, we calculate P and G for all 4 bits simultaneously. P is the exclusive OR of our inputs and G is the end of our inputs. Next, we implement the look-ahead logic. These assignments are the heart of the CLA. Instead of waiting for a ripple, each carry bit is calculated based on the P and G values we just created. Finally, our sum is generated by XORing the propagate signal with the carry in of that stage. This code is clean, parallel, and extremely fast on hardware. Writing the code is only half the battle. We must prove it work using a test bench. In our test bench, CLA_4bit_TB, CLA_4bit_TB, we define our inputs as rect types because we will be driving their values, and our outputs as wire types to observe the results. We instantiate our unit under test UUT, mapping the ports of our 4-bit adder to our test bench signals. To help us debug, we use the monitor command, which acts like live feed in our simulation console, printing the values of A, B, and sum every time they change. Inside the initial block, we apply test vectors. We start with simple zeros. Then we test standard addition like 3 plus 5. We specifically test worst case scenarios like adding 111 with a carry in of 1. This forces the carry to travel across all bits, verifying that our look-ahead logic handles the maximum possible values correctly. The #10 inserts a 10 nanosecond delays between tests, giving the simulation time to resolve. Once all vectors are processed, the finish command stops the simulator. If our monitor shows the correct sums, the CLA is ready for synthesis in quarters. The key takeaway here is parallelism. The code reflects that propagation and generation bits are calculated at the same time for all bits. The design or unit under test is the standard practice of naming the design under test in a test bench, and why we choose specific edge cases like the ones to stress out our logics. Next, let's have a look into multiplier. This is an example of a 2-bit multiplier. Binary multiplication work almost exactly like traditional decimal multiplication, but it is actually much simpler because the only digits are zeros and ones. If you are multiplying A1, A0 by B, B1, B0, you generate partial products just like you would on paper. Multiplying B1 by A1, A0 shifted ones to the left, yielding A1, B1 and A0, B1. Finally, you add the columns together. To get the 4-bit products P3, P2, P1 and P0. To translate the mathematical operation into actual hardware, we map the math directly to the logic gates, generating partial products. Since multiplying any bit by 0 is 0 and by 1 is itself, a simple AND gate perfectly replicates binary 1-bit multiplication. Therefore, calculating A0, B0 is just an A and B gate. To sum the overlapping partial products, like adding A1, B0 and A0, B1 in the middle column, we use half adders and full adders. The sum becomes the product bit, and any carry is passed to the next adder in the chain, as shown here. The exact same shift and add algorithm applies, but it iterates through 4 bits, generating 4 rows of partial products that must be added. When writing HDL code for these circuits, the approach changes depending on the desired level of abstraction. The structural modeling is the lowest level. Here, we can write out the code for every individual AND gate and XOR or AND adder combination to calculate each partial product and sum. It perfectly matches the block illustration, but this is very tedious. For data flow and behavioral modeling, you can simply use the arithmetic multiplier operator as shown here. P is equals to A multiply B. When you compile this abstract A multiply B code, synthesis tools like Intel Quarters are smart enough to automatically map it to the FPGA's built-in, highly optimized hardware multiplier blocks, such as the DSP blocks. The real power here is scalability. As we move from 2-bit to 4-bit or even 64-bit numbers, the structural approach becomes a nightmare of complexity. You would have to manually rewire hundreds of gates. With abstraction, scaling is as simple as changing your vector declaration from 2 bits to 4 bits. The logic, the multiplication operator, stays exactly the same. The synthesis tool, Intel Quarters, does the heavy lifting for you. When you use that multiplication operator, Quarters doesn't just throw random gates together. It is smart enough to map your code to the FPGA's built-in DSP blocks. These are dedicated high-speed hardware cores designed specifically for math. This ensures your design is as small and fast as possible. Finally, for high-performance systems, we can take abstraction one step further by using pipelining. You will cover this in detail in Micro-credential number 3. By adding registers to our behavioral clock, we break long multiplication into several smaller steps across multiple clock cycles. This significantly increases our maximum operating frequency, allowing our digital system to process data at lightning speeds. By focusing on system-level logic rather than gate-level wiring, you reduce human error and speed up your design time. Next, we look at one of the most essential components in digital system, the multiplexer, or simply called as MUX. Think of the mux as a digital switch or a data selector. Its job is to take multiple input and decide which one gets a clear path to the single output. Multiple in, single out. Here is the block representation of a 4-to-1 mux. We have 4 data input labeled as A, B, C, and D, and a single output. But how does a mux knows which input to choose? This is the job of these 2 select lines, select 1 and select 0. Since we have 2 to the power of 2 combination, these 2 bits allow us to choose between 4 inputs. Let's look into the truth table to see this steering logic in action. When S1 is 0 and S0 is 0, the mux chooses A. When S1 is 0 and S0 is 1, the mux chooses B. When S1 is 1 and S0 is 0, the mux chooses C. And finally, when both S1 is 1 and S0 is 1, the mux chooses D. In essence, the select lines act like an address, telling the mux exactly which room to listen to. But what is happening inside that trapezium? If we look into the internal logic, we see a beautiful arrangement of AND and OR gates. Each input is connected to a 3-input AND gates. The other 2 legs of those AND gates are connected to our select lines. Notice the inverters. They ensure that for any given combination of S1 and S0, only one AND gate can be active at a time. All other inputs are effectively blocked. Finally, this path meets at a large OR gate, which passes the successful selected signal through the output. This is combinational logic at its most efficient. Now that we understand the logic of a multiplexer, how do we describe it in Verilog? Depending on your design goals, you can use one of these 3 modeling approaches: behavioral, data flow, and structural. Let's have a look on the first, behavioral modeling. This is often the most intuitive for designers. Using an always block and a case statement, we describe the mux exactly like its truth table. Notice the syntax. When select is 0, 0, out is equals to A. When it is 0, 1, out is equals to B, and so on. Because we are inside a procedural block, our output must be declared as reg type. This is the cleanest way to write a mux, especially as you scale up to 8-to-1 or 60-to-1 selectors. Next is the data flow modeling. Here, we use a continuous assign statement combined with the conditional operator. Think of it like a if-then-else condensed into one line. We nest these operators to check select 1 first, then select 0. While this is very compact and efficient for the compiler, it can become hard to read if you have too many inputs. It is perfect for a simple, fast switching logic. Finally, we have structural modeling. To keep it simple here, we are looking into a 2-to-1 mux. In this style, we aren't writing equation or behavior. We are manually soldering gates together in the code. We define a NOT gate for the select line, 2 AND gates to check the inputs, and an OR gate to combine them. This gives you total control over the physical gate count. But as we discussed with the 4-bit adder, it becomes very difficult to manage as the circuit grows. Whether you use the descriptive case statement or the manual gate level wiring, the synthesis tool will look at your logic and find the most efficient way to implement it on the FPGA. For your lab, I recommend the behavioral case statement. It is easy to read, easy to debug, and very professional. Now that we have studied the adders and multiplexers as individual parts, we are going to combine them into the brain of any processor, the arithmetic logic unit, or as we normally call it as ALU. The ALU is a versatile circuit that performs various mathematical and logical tasks, with a control signal deciding which operators to execute at any given moment. Using behavioral modeling, we can describe a 4-bit ALU very efficiently. Look at our model ALU_4-bit here. We have two 4-bit data inputs, A and B, and a 3-bit selector called select or SEL. The selector acts like a remote control, choosing one of the 8 possible operations. Inside the always block, we use a case statement to define our instruction set. At 000 and 001, we perform basic arithmetic, addition and subtraction. At 010 through 101, we handle bitwise logic and OR, exclusive OR, and a NOT operation on input A. Finally, at 110 and 111, we implement shifting. Shifting bits left or right is a fast way for computers to multiply or divide by powers of 2. Notice that default case at the end. This is a safety feature in Verilog to ensure the output is always defined, even if selectors receives an invalid pattern. To verify our ALU, we use test bench called ALU_4bit_TB. We set our test constant A as 0101, decimal 5, and B as decimal 3, 0011. To verify our ALU, we use a test bench called ALU_4bit_TB. We set our test constant A as 5 and B as 3, represented by binary 0101 and 0011 respectively. Then we cycle through every possible states of the select line. Select 0 up until select 111. Then we monitor the output waveform. Another example is the decoder. A decoder takes an n-bit binary code and activates one of its 2 to the power n unique output lines. It's the perfect tool for a system controller. In one of the labs that you will experience with Lilex 5 project, we use this 2 to 4 decoder to switch between 4 operational modes. When the input is 00, the decoder triggers data collection mode. At 01, it switches to communication mode, and so on, through power management and standby. By using a behavioral case statement, we create a clear hardware map switch for our system states. In the structural approach, we describe the decoder exactly as it appears on the schematic. We manually instantiate 2 NOT gates to invert our selection bits, creating NOT select 0 and NOT select 1. Then we wire 4 AND gates to represent each of our 4 system modes. For example, gate A1 only activates when both inputs are zeros, triggering data collection. This is the most precise way to code, but it's the most time-consuming. If we want a more concise version without manually wiring, we use data flow modeling. Here, we use a sign statement to define the Boolean equation for each output bit. Instead of naming gates, we use the AND and NOT operators. Assign Y, NOT select 1 and NOT select 0. This tells the synthesis tools exactly what logic to build, but in a much more readable equation-based format. Finally, the behavioral approach is what you will use most often in complex designs. Using an always block and a case statement, we simply list the input patterns and their corresponding output modes. For example, here, when the input is 11, the output will be 1000. This is the standby mode. This is the highest level of abstraction. It doesn't tell the FPGA which gates to use, it tells the FPGA what results we want. This makes the codes incredibly easy to scale. if we ever needed to upgrade to a 3 to 8 decoder for more system modes. Imagine a combinational lock. To open it, the order of the numbers you turn matters. The lock has to remember what you did a second ago. This is the essence of sequential logic. Unlike combinational circuits, where the output is determined only by the current inputs, sequential circuits use memory elements. Unlike combinational circuits, where the output is determined only by current inputs, sequential circuits use memory elements. The output now depends on a combination of your current inputs and your previous state. This allows us to build complex systems like counters, timers, and processors. The most critical building block in a sequential design is the D flip-flop. Think of it as a single bit checkpoint. While a basic gate reacts immediately, a flip-flop is age-triggered. It ignores its input until it sees a tick from the system clock, usually the rising age. At the exact moment, it captures the input data and holds it steady at the output until the next clock tick. This synchronization prevents errors by ensuring every part of your circuit moves in perfect lockstep with the clock. RTL, or Register Transfer Level, is the architectural style we use to design this system. In RTL, we view a circuit as data flowing from one set of registers through combinational logic and into another set of registers. When coding RTL in Verilog, we use the always post-edge block. Inside this block, we use non-blocking assignments, represented by the less than or equal symbol. In combinational circuit, we use the standard equals sign for immediate updates. But in sequential RTL, the non-blocking assignment tells the hardware, wait for the clock edge, then update all registers simultaneously. This prevents race conditions, where one part of the circuit accidentally updates before another is ready. Let's look into clock signals in RTL. In digital system, the clock is a global timing reference that coordinates all activities. It is a continuous square wave that toggles between 0, low, and 1, high. A single clock cycle T contains two critical transitions, positive edge and negative edge. Positive edge is the exact moment the signal transits from 0 to 1, or typically termed as the rising edge, whereas the negative edge is the exact moment when the signal transits from 1 to 0, or normally called as falling edge. Unlike the combinational logic, which reacts immediately to inputs, the sequential logic has memory. It retains past states and only updates its output in perfect synchronization with the clock. The most basic 1-bit memory element is the D flip-flop, which ignores its inputs until it sees an active clock edge. At that precise moment, it samples the data and holds it steady. When writing register transfer level RTL code in Verilog, we use the always block combined with the edge-triggered sensitivity list to infer this memory. We also strictly use non-blocking assignment inside these blocks to ensure all registers updates concurrently without race conditions. Positive edge-triggered standard D flip-flops. The vast majority of FPGA designs are synchronized to the rising edge. While you can trigger actual hardware on the falling edge by using always or negative edge clock, doing so in the main design can sometimes complicate clock's domain. However, negative edge is incredibly useful and highly recommended when writing test benches. By applying virtual inputs to your circuit on the falling edge, you guarantee that the signals are perfectly stable by the time the actual hardware samples them on the next rising edge, effectively avoiding setup and hold time violations in your simulation.
Hello, hi. I am Nurul Hazlina binti Nordin from UMPSP Lab, the Faculty of Electrical Electronics Engineering, University Malaysia Pahang Al Sultan Abdullah, the instructor for this course.
Hi, welcome to Chapter 6, RTL Coding Best Practices and FSM Design. In our previous chapters, we focused on combinational logic, where the output is a direct, immediate result of the current inputs. While powerful, these circuits are forgetful. Once the input changes, the previous state is lost forever. To build truly intelligent systems like processors, controllers, and digital watches, we need something more: memory. This chapter marks our transition into sequential logic, the foundation of modern digital architecture. Here, we move beyond simple if-then calculations and introduce the concept of time. In this chapter, we will explore the concept of state. We will learn how a circuit can remember its past by feeding outputs back into its input, creating a history of operations. We will learn about the pulse of the machine. We'll introduce the clock signal, the rhythmic heartbeat that synchronizes every movement within a digital system. And we will also look into the building blocks of these elements. We will dive deep into flip-flops, the fundamental atomic units of digital memory, and see how they differ from the basic latches. We will also master the professional way to describe data flowing between registers using Verilog's non-blocking assignments. Finally, we will combine everything into complex controllers that can navigate through specific sequence, the ultimate brain of any digital project, which is normally termed as finite state machine. Without sequential logic, your computer couldn't count, your phone couldn't run an app, and an FPGA would be nothing more than a collection of expensive gates. By the end of this chapter, you won't just be designing circuits that calculate, you'll be designing systems that think and remember. So, what is finite state machines? A finite state machine is a sequential logic circuit used to control the behavior of digital systems by transitioning between the finite number and internal states based on external inputs and clock cycles. FSMs act as the brain of control logic design, managing everything from simple traffic lights and sequence detector to complex subsystems in picosatellites. Every standard finite state machine consists of 5 key elements. 1. A finite set of states. 2. Inputs that influence transitions. 3. Outputs generated based on states or transitions. 4. Transition logic, also called as next state logic. And 5. A system clock for synchronous finite state machines. Finite state machines are generally categorized into two main architectural types based on how their outputs are generated. In a Moore machine, the outputs depend only on the current state. Because the output is strictly tied to the state register, the output only changes on a clock edge. This provides highly stable, glitch-free signals. The downside is that more finite state machines are generally slower to respond, usually delayed by 1 clock cycle, and may require more internal states. In a Mealy machine, the outputs depend on both the current state and the current input. This allows the machine to react instantly to input changes, making it much faster and potentially requiring fewer states. However, because the output is tied directly to the input, any noise or glitches on the input pins can immediately propagate to the output during the middle of a clock cycle. Some advanced systems use Mealy-Moore hybrid. It uses Moore-style output for stable system responses and Mealy-style outputs for time-sensitive, event-driven feedback. Before coding, FSMs are mapped out visually to understand the required flow. Nodes represents the states and directed arc arrows represent the transitions. More outputs are written inside the state circles, while Mealy outputs are written alongside the transition arc. These look similar to software flowchart, They use state boxes to denote states, decision boxes like a diamond to evaluate input conditions, and conditional output boxes like the oval for mealy outputs. Let's look into an example of a combinatorial clock where you can apply the finite state machine concept. Imagine you are designing a digital lock that only opens when it detects the specific sequence, in this case the sequence of 1, 0, 1, 1. If we use standard combinational logic like the 4-bit AND gate, the lock will only care if all 4 wires were high at the exact same moment. But a keypad doesn't work that way. It receives bit 1 at a time, over a period of time. To solve this, we need a circuit that can remember where it is in a sequence. We need a finite state machine. And FSM tracks its progress using states. Think of this as milestones. As each bit comes in, the finite state machine decides whether to move forward towards the unlocked state or reset because of the wrong digit. There are 2 primary ways to design this: the mealy machine and the Moore machine. In a mealy machine, the output, our unlock signal, is determined by both the current state and the current input. Look at the state diagram here. When we are in the final stage and the last one arrives, the output triggers immediately on that transition. Because the output is tied to the input, mealy machines often have fewer states and react faster. However, this can sometimes lead to glitches if the input signal is noisy, as the output is directly connected to the outside world. Now, let's look at the Moore machine. Here, the output depends only on the state that we are currently in. To detect our 1, 0, 1, 1 sequence, we actually need an extra state. The unlock signal doesn't trigger during the last transition. It triggers only after we have safely landed in the success state. This makes Moore machine much more stable and easier to work with in complex systems, as the output is buffered by the state register and synchronized perfectly with the clock. So to build our lock, we need a map. In FSM design, we call this as state diagram. Each circle or state represents how much of the 1011 pattern we have successfully recognized so far. We start at state 0, the reset state. We are looking for our first one. If we get a 1, we move to state 1. We have found the start. If we get 0, we stay in state 0 and keep looking. If we get a 1, we move to S1. We have found the start. If we get 0, we stay in S0 and keep looking. From state 1, we want a 0. If we get it, we move to state 2. Now that we have 1, 0. But what if we get another one? We don't reset to the beginning. We stay in S1 because that second one could still be the start of the new 1011 sequence. Now at state 2, S2, we have 1, 0. We need a 1 to move to state 3. If we get a 0 here, our pattern is broken and we must reset all the way back to S0. At S3, we are 1 bit away. We have 101. If the next bit is a 1, we have done it. We move to S4 and our unlock output goes high. But look at the 0 transition. If we get 0 at S3, we don't go back to the start. We go to S2 because the sequence we just saw ends in 1, 0, which is the first half of our target. Finally, the S4. The lock is open. To allow for overlapping patterns where the end of 1011 might be the start of the next, we treat S4 like S1. If we get another 0 from here, we are already halfway to our next success. This efficiency is what makes state machines so powerful in high-speed data communication. Take note that this is a Moore machine diagram. Now let's look at the same logic through the lens of a mealy machine. While the Moore machine waits to land in a success state, the mealy machine is much more reactionary. In a mealy machine, you'll notice a different notion on the arrows: input and output. The number here before the slash is what the machine sees, and the number here after the slash is what the machine does. From S0, we sees 1. So we move to S1, and the output is 0. From S1, we see 0. We go to S2, and the output is still 0. From S2, we see another 1. We go to S3, and the output is 0. Pay close attention to this final step. We are in S3, and we receive the final one, where the output is 1. In a more machine, we would move this to an S4 to trigger the output. But in a melee machine, we don't need an extra state. As the machine detects 1, we are moving along the transition arrow. The output instantly flips to 1. The success happens on the way to the next state. Because the output is a direct function of the current state and the current input, we have detected the full 1011 sequence using only 4 states instead of 5. Notice that where the 1 is located in our diagram, it's attached to the arrow moving out to S1. This is the hallmark of melee design. The moment that the third one hits the input wire, the lock opens. It's faster and uses less hardware, but it requires us to be careful with our timing, as any noise on the input line could momentarily flicker our output, causing glitches in our digital system design. To bridge the gap between a visual diagram and Verilog code, we use a state transition table. This table is the mathematical blueprint that a synthesis tool uses to build the actual logic gates. Let's take the example of the Moore machine. In a Moore machine, the output depends solely on the current state. We will use 3 bits for the state encoding to accommodate our 5 states: state 0, state 1, state 2, state 3, and state 4. Before we write a single line of Verilog, we need to translate our visual state diagram into a formal state transition table. The table is essentially the DNA of our state machine. It maps every possible combination of our current situation and our next move. Look at this structure. We have our input, our current state, and our next state. For a Moore machine, we also have a dedicated output column that is tied strictly to the current state. Notice the first few rows. If we are in state 0 and the input is 0, the table tells the hardware to stay in state 0. But if the input flips to 1, the table points us to state 1. This is how the logic of the sequence is stored. If we are in state 1 and the input is 0, we move to state 2. But if we notice the input is 1, we stay in state 1, moving to state 2. If we see the input is 0, we go to state 0. But if we see the input is 1, we go to state 3. And when we are in state 3 and the input is 0, we go to state 2. If the input flips to 1, we move to state 4. The most important part of a Moore table is the output. Look at state 4. Regardless of whether the input is 0 or 1, the output is 1. Why? Because in a Moore machine, reaching the state is the success. The output doesn't care about the input bit at the exact moment. It only cares that the success state has been reached. Take note that every input state combo has a defined destination. The output column only changes when the current state changes. Now that the table is complete, we are ready for the Verilog implementation. Would you like to start the state encoding using parameters or the 3-block logic? Next state register output. Now that the table is complete, we are ready for the Verilog implementation. When translating NFSM into Verilog, it is an industry best practice to use symbolic constant using local parameter to name your states. for example, idle, start, done, success, is standard FSM is typically implemented using 3 distinct blocks of code. The first one is the state register, an always positive edge clock block using non-blocking assignment that simply updates the current state to the next state at every rising edge. The next state logic, a combinational always block that uses a case statement. It looks at the current state and the inputs to evaluate what the next state should be. And the output logic block, another combinational block or assign statement that turns output signals on or off depending on the active state and inputs if it is a Mealy machine. Now let's look how we translate our mod transition table into clean Verilog code. We use the 3-block style which separates memory from logic. First, look at the next state logic. Notice the case statement. It follows our truth table row by row. Now look at the state register block. This is the only sequential part of the code. It uses the non-blocking assignment to move the next state into the current state every time the clock ticks. Finally, look at the output logic at the bottom. Notice it is completely separate from the input X. It simply asks, are we in state 4? If yes, the lock opens. This separation is why more machines are so stable. The output only changes when the state registers updates on the clock edge. Now let's look into the more machine, which is organized into the 3-block style. The header and state definition. Clock reset and input X. The clock synchronizes the system. The reset puts us at start, and our X is our serial 1011 data stream. We define states S0 to S4 as constant local parameter. This makes the code readable. Instead of seeing 3D3, we see state number 3, for example. And we declare reg 3-bit state next. We need 3 bits to store up to 5 states. State is where we are now. Next is where we will be after the next clock tick. Now we look into the first block, next state logic, combinational logic. Always, this block calculates logic instantly. It doesn't wait for a clock. The case statement. It looks at the current milestone we are in. And the ternary. This is the shorthand of if-else. If X is true, meaning to say X is 1, the results is state 1. And so on. Now, moving to the state register block, the sequential block. Here, take note that we are using pause edge, positive edge clock. This is the heartbeat. The machine only moves on the rising edge of the clock. And take note that we are assigning a non-blocking assignment here. This is crucial for sequential logic. It ensures the state updates only when the clock edge hits. And take note of the non-blocking assignment used here. This is crucial for sequential logic. It ensures the state updates only when the clock edge hits. Moving on to the final block, the output logic, combinational logic. This is the advantage of using more machine. The output Z is high only if we are sitting in state 4. It doesn't care what the input X is doing right now. Now, contrast that with the Mealy machine. You will immediately notice the code looks a bit more crowded inside the case statement. In a Mealy machine, the output Z is tied to the transition, not just the state. Because of this, we must use if-else blocks inside every state. Look at state 3. We check input X immediately. If X is 1, we don't just set the next state. We also set our output Z to 1, right there in the same block. This means the Mealy machine is listening to the input in real time. The moment that final one hits the wire while we are in state 3, the output triggers. It doesn't wait for the next clock edge to land in a new state. While this makes melee machine faster and allows it to function with one fewer state than the more machine, it also means the output can be jittery if the input signal isn't perfectly clean. Choosing between these two often comes down to the trade-off between speed and stability.
Hello, hi. I am Nurul Hazlina binti Nordin from UMTSP Lab, the Faculty of Electrical Electronics Engineering, University Malaysia Pahang Al Sultan Abdullah, the instructor for this course.
Hi, we are now in Chapter 7, Functional Simulation. Before we ever compile our code into physical FPGA chip, we must mathematically prove that our logic works exactly as intended. Today, we are exploring functional simulation and verification strategies, the critical steps that save engineers countless hours of hardware debugging. FPGA do not synthesize test codes into physical hardware. Because of this, verification relies on creating simulated virtual lab bench or test bench. The standard workflow starts with writing your Verilog RTL module, known as device under test or sometimes unit under test, simply denoted as DUT or UUT. Next, you will write a separate test bench file that instantiate the DUT and apply virtual input stimuli. Using tools like Model Sim, we compile these files to check for syntax errors, and then run the simulation to observe the circuit's response in real time. FPGAs do not synthesize test codes into physical hardware. Because of this, verification relies on creating a simulated virtual lab bench. The standard workflow starts with writing your Verilog RTL module, known as the device under test or DUT. Next, you write a separate test bench file that instantiates the DUT and applies virtual input stimuli. Using tools like Model Sim, we compile these files to check for syntax errors, and then run the simulation to observe the circuit's response in real time. This is an example of a signal generator. Once the simulation is complete, we turn into waveform analysis to visually confirm signal transitions over time. We use this to verify critical timing relationship, ensuring signals meet setup and hold time relative to the system clock. We also check our control signals, like confirming that resets properly initialize the system and clock pulse consistently. Finally, we validate the output logic, tracing signal changes across clock cycles to spot glitches or incorrect behavior before they become physical hardware bugs. When a simulation fails, systematic debugging in Model Sim is key. First, hunt for rate X values, which indicate unknown or uninitialized signals, and Z value, which point to floating or unconnected wires. To make verification scalable, industry practice dictates writing self-checking test benches that automatically flag output mismatches. Finally, you can use dump file command to export your simulation data into a VCD file, allowing for deep waveform analysis in advanced viewing tools. Master these steps and your hardware implementation will be right the first time. While looking at waveform is great, manual inspections is tedious. To automate the process, we use monitors and assertions. Verilog system tasks like display print one-time debugging messages, while monitor continuously tracks specified variables, printing a new message whenever a value changes. For formal checking, we use assertion. An assertion is an automated runtime check embedded in your code. If a condition fails, for example, if a state machine enters an illegal state, the simulator immediately throws a fatal error, giving you instant bug detection. Writing FSM code is one thing, but making it hardware safe is another. One of the most common mistakes is the logic trap, specifically creating race condition. Look at the difference between our assignment operators. In our sequential block, we use non-blocking assignment. This is vital. If you accidentally use the blocking equal sign, the synthesis tool might update your current state before other parts of the circuit have finished reading it. This creates a race where the output becomes unpredictable. Another trap is the melee glitch. Because the melee output is directly connected to the input wire X, any tiny static or noise on that wire will show up instantly on your unlocked signal. This is why we often flop the register, the output or noise on that wire to turn a messy, unsynchronous signal into a clean, synchronous one. So how do we know our 1011 detector actually works? We use test bench. Think of a test bench as a virtual laboratory. It's a piece of Verilog code that doesn't go onto the chip. Instead, it wraps around our design to provide the stimulus. In this verification phase, we simulate the clock and feed in a specific serial stream, like 11011. We look for two things in the waveforms. First, the functional accuracy. Thus, the output Z actually goes high when the 1011 pattern finishes. And secondly, we look for the overlapping handling. If we feed in, say for example, 101111, does the machine detect the pattern twice or don't? As you can see from the waveform, the melee output usually fires slightly earlier than the more output. This golden waveform is our proof of design. Only after the simulation passes every test case do we move forward to physical implementation on the FPGA. As an engineer, you have two bosses, the logic and the user. Verification is how you satisfy the logic. You run a test bench to prove that your state machine transitions from state 3 to state 4 exactly when the bits 1011 arrive. If your simulation shows a 1 at the right nanosecond, you have verified your design. But you aren't done until you validate. This happens when you load that code onto an FPGA and hook it up to a real keypad. Does the lock stay open long enough for someone to turn the handle? Does it ignore electrical noise from a nearby monitor? Verification proves your mathematics is correct, while validation proves your solution works in the messy real world. Writing code is only 30% of the job. The other 70% is verification. To ensure our 1011 sequence detector is a bulletproof, we don't just run and see. We build a structured environment using 4 key components, as will be discussed here. First, the stimulus. This is the input generator of our test bench. We don't just feed in a random string of bits. We create a deliberate test case. We toggle the reset. Then we feed 1011. Then we try a false sequence like 1010 to make sure that the lock doesn't open. A good stimulus checks every corner of our state diagram, including those tricky overlapping patterns like 101111. Secondly is the waveform. This is the digital X-ray of our circuit. By looking at the timing diagram, we can see exactly when the state changes. Is the more output lagging by 1 clock cycle, for example? Is the melee output firing too early? Waveforms allow us to see the inner life of our FSM and catch timing glitches that a simple pass or fail test might miss. Third is the monitors, the observers. While we can watch waveforms, a monitor automates the process. This is a piece of code in the test bench that listens to output and prints messages to the console. Instead of squinting at a line, the monitor tells us, at 15 nanosecond for example, pattern 1011 detected. It records the history of the simulations, so we can review exactly what happened during a long test run. And finally, the assertions, the logic guard. These are the security guard of our code. An assertion is a statement that must be true. For example, if we are in state 4, the output must be 1. If the hardware ever violates this rule, the assertion fires and stops the simulation immediately. It's the most powerful way to catch bugs automatically without having to manually check every single line of the waveform. By combining these 4 tools, we move our guessing that our 1011 detector works to mathematically proving it. Now that our FSM is verified, we are ready to move from the virtual simulator to the physical FPGA.
Hello, hi. I am Nurul Hazrina binti Nordin from UMTSA STEM Lab, the Faculty of Electrical Electronics Engineering, University Malaysia Pahang Al Sultan Abdul Rahman, the instructor for this course.
Hi, welcome to chapter number 8, Logic Synthesis and Gate Level Mapping. In this chapter, we will look into how abstract RTL Verilog code is transformed into a gate-level netlist and mapped to physical FPGA hardware, focusing on the synthesis flow, optimizations, and the quarters prime environment. Up until now, we have lived in a world of text and simulations. But how does a text file actually turns into a physical circuit? This is the process known as logic synthesis and mapping. Let's follow the life cycle of a design as it moves through the compiler. It's all started with your RTL code. Once you have completed your Verilog code, and when you hit compile, the tool performs parsing optimization. In this stage, it reads your Verilog like a grammar teacher, checking for syntax error. Once the code is legal, the tool performs optimization. It looks for ways to simplify your logic. For example, if we have added 0 to a number, the tool simply removes that adder to save space. Moving on to the next step, technology mapping. This is the most critical step. The compiler takes your optimized logic and looks at the library out of the specific FPGA you are using. It asks, how do I fit this 4-bit ALU, for example, into the specific lookup tables and registers available on this Intel or Xilinx chip? It's like the high-speed game of Tetris, fitting your logic into the physical constraints of the hardware. Next is the gate-level netlist. Gate-level netlist is the results of the mapping earlier. At this stage, your always blocks are gone. In their place is a massive web of specific hardware primitives. The netlist is often saved as .v file, but instead of readable code, it contains thousands of instances of specific FPGA components wired together. This is the final blueprint of your circuit. Moving on is the implementation stage. Here, the software performs place and route. Now that we have the blueprint, we need to decide where everything goes. This is implementation, which consists of fitting, placement, and routing. Placement decides which specific corner of the chip will hold your ALU, while routing chooses which microscopic copper wires will connect those parts. While routing chooses which microscopic copper wires will connect those parts. The tool tries to keep related parts close together to minimize wire length and maximize speed. Moving on is the programming file stage. The programming file, usually a .sof for Intel or a .bit for Xilinx. This isn't code, it's binary image of how every switch and connections on the FPGA should be set. When you flash this file onto your board, the FPGA physically reconfigures itself. Your Verilog code has finally become a living, breathing hardware circuit. Understanding this flow is essential for debugging. If your design doesn't work, the problem could be in your RTL, or it could be in the timing violation that occurred during the place and route stage. Knowing where to look is important for a professional IC design engineer. In general, this topic is about RTL Verilog code is transformed into a gate-level netlist and mapped to the physical FPGA hardware, focusing on the synthesis flow optimizations and the quarters prime environment. In another perspective, the logic design flow is a critical process that bridges the gap between software-like code and actual physical hardware. It starts with your RTL code. The synthesis tool first parses the Verilog to check for syntax errors and builds an internal representation. It then optimizes the design, performs technology mapping to map the abstract logic directly to FPGA primitives, and generates a gate-level netlist. Finally, the implementation stage fits, places, and routes these components on the silicon chip, leading to the generation of the final programming file. The logic synthesis flow is the critical process that bridges the gap between software-like code and actual physical hardware. It starts with your register transfer level code. The synthesis tool first parses the Verilog code to check for syntax errors and builds an internal representation. It then optimizes the design, performs technology mapping to map the abstract logic directly to the FPGA primitives, and generates gate-level netlists. Finally, the implementation stage fits, places, and routes these components on the silicon chip, leading to the generation of the final programming file. To understand how an FPGA works, let's look under the microscopic skin of the silicon. If we imagine entire FPGA is a massive programmable city, the CLB or the configurable logic block is the basic building blocks, like a single apartment unit. But what's inside this cell? Every CLB contains the fundamental unit of digital logic. First, there is this lookup table, then the brain of the cell. It's a small piece of memory that can mimic any logic gates, an AND, or even a 4-to-1 multiplexer. Next is the flip-flop. This is the memory of the cell. It allows the chip to hold onto a bit of data until the next clock tick. Finally, the multiplexer. This acts like a switchboard, deciding whether the signal should pass through as a raw logic or be stored in a memory. During the synthesis phase, the compiler actively optimizes your design to improve both performance and area. It uses automatic techniques like constant folding to simplify static mathematical expressions at compile time, and dead code removal to strip away any logic that will never be activated. It also employs resource sharing to reuse hardware blocks like adders and retiming to move registers across logic boundaries to minimize critical path delays. After these optimizations, technology mapping translates your abstract logic into specific FPGA resources, such as lookup tables, flip-flops, memory blocks, and carry chains. The direct output of the technology mapping is the gate-level netlist. This is typically a lower-level Verilog file or an EDIF file. It is no longer high-level behavioral code, rather it is a physical hardware blueprint that details exactly how the actual logic gates, multiplexers, and registers are wired together inside the FPGA. The netlist is incredibly useful because it can be used to run a post-synthesis gate-level simulation to verify that the newly optimized hardware still maintains the exact functional behavioral you intended. It is no longer high-level behavioral code. Rather, it is a physical hardware blueprint that details exactly how the actual logic gates, multiplexers, and registers are wired together inside the FPGA. The netlist is incredibly useful because it can be used to run post-synthesis gate-level simulation to verify that the newly optimized hardware still maintains the exact functional behavior you intended. In the industry, Intel Quartus Prime is the comprehensive environment used to synthesize these designs for devices like the DE10 Lite board. A critical part of using quarters is correctly analyzing its compilation report and synthesis warning. For example, a latch inferred warning often means you miss an else condition, and a combinational loop warning indicates an unstable feedback path missing a register. Additionally, Quarters TimeQuest Timing Analyzer generates essential report on setup and hold time violation, slack, and the maximum operating frequency to ensure your physical circuits will meet all the performance constraints. In the first stage of the synthesis flow, the compiler acts as a translator. It must first convert your human-readable Verilog code into a structured format that a machine can manipulate. This process is divided into three critical phases: syntax checking, AST generation, and elaboration. Let's have a look in the syntax checking, lexical and syntactic analysis. The moment you start synthesis process, the tool performs syntax checking. Think of this as a rigorous grammar check. First, the lexers break your codes down into tokens. The keyword like module, always, and input. Then, the parsers ensures these tokens follow the rules of the Verilog hardware description language. If you missed a semicolon, for example, you forgot an end module tag, or use a reserved keywords as a variable name, the tool will stop here. It refuses to move forward until the grammar of your hardware is perfect. Once syntax is verified, the tool creates abstract syntax tree or AST. This is the hierarchical, tree-like representations of your code structure. In this tree, the root is the module itself, and the branches represents your logic blocks, such as always statements or assigned declarations. The AST strips away unnecessary text like comments and white spaces, focusing purely on the logical relationship between your signals. This tree is the internal map the compiler uses to understand the flow of your design before it starts building gates. The final and the most complex part of parsing is elaboration. During this phase, the tool goes beyond simple text and begins to understand hardware hierarchy. If your design has a top-level module that calls 3 smaller submodules, elaboration is the process of plucking those modules from your library and wiring them together. The tools also resolves parameters. For example, if you define a generic n-bit adder and set n to 8, elaboration creates the specific 8-bit version. By the end of the stage, the compiler has a compiled logical view of the entire system, ready to be optimized and mapped to physical silicon. In summary, syntax checking validates Verilog rules and keywords, checking the spelling and grammar of a book. AST generation creates a logical tree of the code outlining the chapters, and elaboration connects modules and expands parameters, building the physical structure based on the outline. It is important to remember that a design can pass syntax checking but fail during elaboration. This happens if you reference a module that doesn't exist or create circular dependencies where two modules call each other. So it is important for you to know these processes while designing your digital system in Verilog environment. Masteries of these stages allow you to debug your design much faster when the compiler throws an error. Let's take a closer look at what happens during the RTL optimization phase. The synthesis tool acts like an intelligent editor to your code. First, it performs constant folding, which simplifies mathematical expressions involving constant at a compile time. For instance, it automatically turning 3 plus 5 into an 8, so it doesn't waste hardware calculating it during the runtime. Second, it performs dead logic removal, where it completely strips away any logic path or branches that will never be activated, saving precious space on the chip. In another work, logic optimization is where the synthesizer looks for ways to achieve the same output using fewer resources. It uses Boolean algebra to simplify equations. For instance, if you have circuits that calculate A and 1, the tool knows that the output will always be just A, so it deletes the AND gate entirely. It also performs constant propagation. If an input is tied to ground or VCC, the tool calculates the ripple effect through the logic and removes any gates that becomes dead or redundant. This reduces the area of your chip and significantly lowers power consumption. Now that the logic is as small as possible, we move into technology mapping. A generic AND gate doesn't exist on an FPGA. Instead, FPGA uses lookup tables. During mapping, the tool groups your optimized logic into these lookup tables. A single 6-input lookup table can replace dozens of individual gates. The goal here is to minimize the number of levels or hops between registers. Fewer levels means the signal travels faster, allowing you to increase your system's clock speed. Once optimized, the abstract mathematical operations must become real hardware through technology mapping. During this step, the synthesis tool takes your abstract logic, like ANDs, OR, or additions, and maps them directly to the physical primitives available on the FPGA fabric. Simple combinational logic is mapped into lookup tables. Sequential logic is mapped to flip-flops. And heavy arithmetic operations are routed to dedicated hardware like digital signal processing or DSP blocks. And storage are mapped to block RAMs. The final output of this stage is gate-level netlist. This is a structural verilog that represents your design using actual primitives or building blocks of the specific FPGA you chose. At this point, your hardware-level case statement and if-else blocks are gone. They have been replaced by a massive list of wires and specific hardware instances. This netlist is the master blueprint that Place and Route tool will use to decide exactly where to put each component on this silicon fabric. The direct output of technology mapping is the gate-level netlist, typically generated as lower-level verilog.v file. It is crucial to understand that this file is no longer high-level behavioral code. It is literally physical hardware blueprint. It describes the exact hardware structure at the gate level, showing exactly which lookup tables, multiplexers, and registers have been utilized and how they interconnect to form your specific design. With the netlist generated, the software moves into the implementation phase, often called place and route or fitting. Fitting maps the logical resources from your netlist into the actual physical location inside the FPGA fabric. During the placement start stage, the software calculates the optimal physical positions for each logic block. The goal here is to balance resource utilization while keeping connected components physically close to one to another to minimize delay. After all the logic blocks are placed, the routing stage begins. The synthesis tool establishes the physical wiring connections between every logic elements using the FPGA programmable interconnect matrix. This stage is incredibly critical because even if your RTL code is perfectly correct, poor placement or inefficient routing can cause signal delays, leading to timing violations that will stop your hardware from functioning at its targeted speed. The final stage of this implementation process is generating the device configuration file. This file contains the exact binary data required to program the FPGA's internal logic, routing, and I/O structure. If you are using Intel Quartus for the E10 Lite board, it generates the SRAM object file, or .sof for temporary programming via a USB cable during testing. For permanent memory storage, a .pof file is used, whereas Xilinx system generates a .bit file. It is important for you to understand the overview of the FPGA implementation phases, as it will give you a better idea upon analyzing the implementation post-processing reports generated by the FPGA simulation tools. It is important for you to understand the implementation phases in FPGA development. Why is this important? Because as a digital IC designer, your job does not stop at writing Verilog code or verifying waveform in simulations. In earlier labs, you focus on writing HDL codes, running simulations, observing waveforms. That is only part of the design process. Simulation tells you, is my logic functionally correct? But in real hardware, what we must do, we must also ask, will this design work reliably at the required speed? Is it efficient in terms of hardware resources? When you compile your design in quarters, several important steps take place. The synthesis, fitting and placement, and routing, timing analysis, bit stream generation. After compilation, quarters generates several reports: resource utilizations, timing analysis, critical path, warnings and errors. These reports are not optional reading, they are essentials. They tell you if your design is too slow, if timing violation exists, if resources are overused, if your design is reliable in real hardware. So, as digital designers, you must move from just looking at waveforms to analyzing implementation reports and optimizing design. Because in real-world engineering, a design that works in simulation but fails timing in hardware is considered not a valid design. So, understanding FPGA implementation phases will help you to interpret quarters reports, debug real hardware issue, and improve your design performance, and ultimately become a complete digital system designer. Now, let's take a look at a sample of quarters compilation report, and more importantly, how to interpret it. First, we see flow status, in which it is stated as successful. This means the design has compiled without any fatal errors. A bit stream has been generated. However, this does not guarantee that the design is correct or optimal. A successful compile can still have functional issues, timing violations, and poor design practices. Next, we have the Quarters Prime version 2.22.1 standard. This is important for reproducibility, compatibility, and debugging differences between tool versions. Now, look at this total logic element, 1,234 out of 50,000, equivalent to 2%. These tell us that your design is using only 2% of the available resources. So, in terms of area, the design is very small. This is good, but also tell us that we have 98% room to scale. Then look at this PLL usage, where the total PLL is 25%. This means one phase lock loop is used, typically for a clock generation or frequency scaling. This is important because PLLs are limited hardware resources. Now, the most critical parts are warnings. We see here latch inferred and signal is assigned but not used. So what does this mean? When latch is inferred means it usually happens due to incomplete assignments in combination logic. This is often unintentional. This, however, can lead to unpredictable behavior. Whereas signal assigned but not used indicates redundant or unused logic. This may point to coding mistakes, incomplete designs, or poor optimization. So when reading a compilation report, don't just look for success. You must ask, are there warnings? Is the design efficient? Are there hidden design issues? Because these reports give you insight into what your hardware is actually doing, not just what you think it is doing. Now let's talk about one of the most important concepts in digital design, the trade-off. In any FPGA design, we usually care about two things. The first one is the area, the hardware usage. The goal is to minimize resource usage, and the matrix that is normally associated is the logic elements, registers, memories, whereby the constraint is limited chip size. We want the design to use as little hardware as possible. And secondly is the speed, the performance. The goal is to maximize operating frequency. The matrix that is normally associated is Fmax or maximum frequency. It is also related to critical path delay, and the constraint is always the timing closure. We want our design to run as fast as possible. However, these two goals often conflict. If you try to increase speed, you may need more resources, more registers, pipelining in which the area increases. If you try to reduce areas, you may simplify logics in which you are compromising on the speed, where the speed decreases. So, design is always a balance act. For example, a simple combinational logic requires small area but slower. A pipeline design is faster but uses more hardware. So, as an IC design engineer, your job is not just to make the design work, but also your job is to optimize for area based on constraints. If the system is resource limited, optimize for area. If the system is performance critical, optimize for speed. So when you look at Quartus report, always think, am I using too much hardware? Or can I make this design faster? Because good digital design is not just correct, it is efficient and optimized. Logic synthesis is often mistaken for a simple press of a button process. In reality, it is a sophisticated, iterative conversation between you and the synthesis tool. To wrap up this chapter, let's look at the synthesis feedback loop, the engine that drives every high-performance digital design. It begins with translation. This is where the tool takes your abstract intent, your Verilog code, and combines it with your timing constraint, the SDC file. The tool needs to know not just what the logic does, but how fast it needs to be. It translates your behavioral descriptions into a generic web of Boolean equations. Next is mapping. As we discussed in our workshop analogy, the tool now takes those generic equations and fits them into the physical FPGA resources. It decides exactly which lookup tables, ALMs, and registers will execute your code. This is the moment of your design becomes technology dependent, locked into the specific DNA of your chip. Once mapped, the tool performs the classic engineering trade-offs, area versus speed. If you demand maximum speed, the tool might duplicate logic or use more parallel paths, increasing the area or footprint. If you need a small area, the tool will prune the design and potentially slowing down the system. The synthesizer is constantly balancing between these two scales to find the sweet spot for your specific constraints. A good example is the ripple carry adders and carry look ahead adders discussed in previous micro-credential course. Finally, we reach the most important part of the loop, the feedback. The tool generates reports and warnings. This is the health check of your design. Did you meet the timing? Did you run out of lookup tables? A critical warning isn't just an error. It is a signal that you need to go back to the start. You might need to rewrite your Verilog, adjust your constraints, or change your optimization setting. And so the cycles repeat. You refine, you resynthesize, and you optimize until the reports are clean and the timing is close. Mastering these loops is what turns a Verilog coder into a true FPGA designer. To conclude our look at the synthesis flow, are you ready to dive deep into Chapter 9, Static Timing Analysis, where we will learn exactly how the tools calculate speed side of this trade-off?